We're about to dive into one of the most beautiful and far-reaching ideas the human mind has ever really grasped. It's a single principle, so simple it's almost poetic, yet so powerful it controls everything, from an apple falling from a tree to the grand cosmic dance of entire galaxies. This is the incredible story of the law of gravitation.
For, well, basically all of human history, this was one of the biggest questions out there. I mean, you could look up and see the planets wandering across the night sky, but what was pushing them? What invisible tracks were they following? So together, let's follow the clues and crack this ancient cosmic puzzle.
Okay, so our story really kicks off with a massive shift in how we even approach the question. The old ways of just, thinking about the heavens were about to get a huge, radical upgrade. For centuries, people just had deep philosophical arguments about how the planets should move. But then, in the 16th century, this astronomer, Tycho Brahe, came along with a revolutionary idea. He said, let's stop arguing and start measuring. He was convinced that the only way to find the real truth was with careful, precise data. And that right there was a game-changing insight that actual experiment is a much better tool than just philosophy for understanding how nature works. So Tycho Brahe spends his life creating these enormous volumes of the most accurate data the world had ever seen, just a treasure trove of numbers. And after he died, all that data fell into the hands of a brilliant mathematician who's about to find the secret pattern hidden inside all of it, a guy named Johannes Kepler. So Kepler dives into Tycho's tables, and he pulls out 3 beautifully simple rules. First, he realized planets don't move in perfect circles, they move in ellipses, with the sun off to one side. Second, they actually speed up when they get closer to the sun and slow down when they're farther away. And third, there's this perfect mathematical link between a planet's year and its distance from the sun. But, and this is the absolute key, these laws were a perfect description of how the planets moved, but they gave zero clue as to why.
And now the stage was set. All the clues were on the table for one of the greatest minds in history, Isaac Newton, to put it all together into one single universal explanation.
You see, the old theories imagined that invisible angels were literally pushing the planets along their paths. But Newton, building on Galileo's idea of inertia, that an object in motion stays in motion, had this brilliant flash of insight. He realized you don't need any force pushing the planet forward at all. A planet would just coast in a straight line forever. So the only thing you need to explain the orbit is a force that's constantly pulling it sideways, directly toward the sun. The angels weren't pushing from behind, something was pulling from the center.
And this led Newton to his universal law. The force of attraction between any two objects just depends on how massive they are and how far apart they are. And crucially, it gets weaker as the square of the distance increases. That's the famous inverse square law. It was simple, it was elegant, and it worked for everything, everywhere. This was it. This was the answer to the ancient puzzle.
Now to prove it, Newton did this absolutely masterful calculation. He knew an apple falls about 16 feet in the first second. He then figured out how much the moon falls away from a perfectly straight path in that same second. The answer? About 1/20th of an inch. Now the moon is 60 times farther away from Earth's center than the apple, and according to his inverse square law, that means the force should be 60 squared, or 3,600 times weaker. And what do you get when you divide 16 feet by 3,600? Yep, you guessed it, 1/20th of an inch. The math was perfect. The force pulling the apple to the ground was the exact same force holding the moon in orbit. So what is an orbit, really? Well, think about it like this. You fire a cannonball, and it falls 16 feet in the first second. Simple enough. But the Earth is curved, right? If you could fire that cannonball at a ridiculous speed, say 5 miles per second, then in the time it falls those 16 feet, the Earth's surface has curved away by the exact same amount. It's constantly falling, but it never actually gets any closer to the ground. That perfect balance is exactly what an orbit is. It's how astronauts stay up in space.
A really great scientific law doesn't just explain what you already see, it lets you predict things you haven't seen yet. And Newton's law? It turned out to be an absolutely incredible tool for discovery.
Let's talk about the tides. For ages, the big mystery was why we have 2 high tides every day, not just one. Newton's law nailed it. The moon's gravity pulls strongest on the water closest to it, right? That creates one bulge. But, and here's the clever part, it also pulls harder on the solid Earth than it does on the water on the far side. So it's basically pulling the planet away from the water on the other side, creating a second bulge. This explained the 12-hour tidal cycle perfectly.
And the predictive power was just stunning. Back in 1676, astronomers noticed Jupiter's moons weren't always on schedule. Sometimes they were early, sometimes late. But the law of gravity wasn't wrong.
It was showing them something amazing. The time it took for light to get from Jupiter to us. It gave us our first real estimate for the speed of light. Fast forward a couple centuries, and there's another puzzle. The planet Uranus wasn't following its predicted path. It was wobbling. Two astronomers used Newton's law to calculate where an unseen planet must be, pulling on it. They literally told observatories, hey, point your telescope right here. And boom, there it was, Neptune, a whole new world, found with nothing but a pen and paper.
And the law just doesn't stop. It perfectly describes how double stars whirl around each other. It explains why stars gather together in these huge, dense swarms called globular clusters. And it's the fundamental force that sculpts and holds together entire galaxies, stretching across hundreds of thousands of light years. From our backyard solar system to the biggest things we can see, it's all the same universal dance, governed by the same simple rule.
But for all its incredible success, Newton's theory of gravitation actually cracked open a whole new set of even deeper, more profound mysteries.
See, Newton's equation had this number in it, the gravitational constant g, but he had no idea what its value was. It took this unbelievably delicate experiment by Cavendish, who measured the tiny gravitational pull between lead balls, to finally nail down the number for g. And once we knew that constant, we could suddenly do something just astounding. For the very first time in human history, we could weigh the entire planet Earth.
But what is gravity? What's the mechanism? What's actually causing this pull? Newton himself had no idea. He famously said he framed no hypotheses. He was basically content to have found the mathematical law that described how it all works without getting tangled up in the why.
Now, people have certainly tried to invent a mechanism. There was this popular idea in the 1750s that space was filled with tiny particles flying everywhere, and the sun would block some of them, casting a particle shadow that would push the Earth towards it. Sounds clever, but it has a huge flaw. A planet moving through space would hit more particles on its front side, creating a drag that would make it spiral into the sun. To this day, no mechanical model has ever worked.
But this is where the mystery gets truly mind-boggling. Let's compare the gravitational pull between two electrons to their electrical repulsion. The electrical force is stronger, a lot stronger. It's stronger by a factor of 4 with 42 zeros after it. That number is so huge it's hard to even wrap your head around. And this isn't just a random fluke. It's a fundamental feature of our universe, and we have absolutely no clue why gravity is so fantastically, almost absurdly weak.
And here's one more deep puzzle. Why do astronauts feel weightless? Well, it's because gravity's pull is perfectly, and I mean perfectly, proportional to an object's mass, its inertia. So a more massive spaceship needs a stronger pull to stay in orbit, and gravity provides exactly that much more force. This perfect balance, which has been tested to 1 part in a billion, means that everything inside the spaceship, the astronaut, pen, whatever, is all falling at the exact same rate. And since nothing is pushing up on them from below, they feel like they're floating. It's that sensation of continuous freefall.
For more than 2 centuries, Newton's law was the undisputed champion. But it wasn't the end of the story, not by a long shot. The story was about to take another truly revolutionary turn.
And that turn was Albert Einstein. He didn't just tweak the rules, he completely rewrote them. He imagined a universe where gravity wasn't a force at all, but a curve in the fabric of space and time. So in Newton's world, if the sun just vanished, its gravity would disappear everywhere instantly. But Einstein said, hold on, nothing can travel faster than light. So the news of the sun's disappearance would ripple outward at the speed of light. And what fuels those ripples? For Newton, only things with mass. But for Einstein, gravity affects anything with energy, which even includes massless beams of light. A wild idea that was proven true when we saw starlight literally bending as it passed by the sun.
So you see, our understanding has been on this incredible journey. From Kepler's simple, elegant orbits, to Newton's universal force that connected the heavens and the earth, to Einstein's mind-bending curved space-time. But the journey is not over. The biggest challenge in all of physics today is trying to unite gravity, the grand architect of the cosmos, with the bizarre rules of the quantum world that govern the very small. The universe's most elegant law is still holding on to its deepest secrets. So what is it? Is gravity a force? Is it carried by a particle? Or is it something we can't even begin to imagine yet? That is the next great cosmic puzzle.